Hello and welcome to this video tutorial. In the last episode, we looked at the difference between parametric and non-parametric tests. So today we are going to look at the different types of the parametric and the non-parametric tests that are available. We shall also be looking at the alternatives of the parametric tests, and we are also going to look at this different steps that you should use or should go through to ensure that you select the most appropriate statistical test for your data. So let's get started. For you to be able to choose the most appropriate test for your data, there are three key questions that we are going to ask ourselves. The first question we are asking ourselves is, what type of data do you have? Is it categorical data? For example, marital status, where we have married, single and separated? Do you have gender, which is male, female? Do you have BMI categories, e.g. underweight, normal or overweight? Is it disease status, which is maybe positive, negative? Or you have numerical data as age, weight, height? Remember that this can also be categorized into meaningful categories. If you have numerical data, you can also generate meaningful categories from it. The second type of question we are asking ourselves is, how many groups do we have? In the previous example of marital status, if it is captured as married, single and separated, those are three groups or response levels. If we have gender as captured as male and female, then we have two groups. In this case, marital status and gender are variables, whereas the weight was captured at the groups or responses. The last question is, what is this test supposed to do? Is it to establish a relationship? We want to see, as age increases, how does height change? Or you want to look at a relationship between two categorical variables, marital status versus BMI. It could also be maybe gender versus disease status. You want to see whether is disease status different for the males and females. The test could also be aimed at establishing a difference. For example, gender and disease status. Or you want to see gender versus weight. At this point, we need to differentiate between independent or predictor variables and the dependent or outcome variables. In this example of gender versus disease status, gender is the independent variable, whereas disease status is the outcome. An outcome is one which depends on the other. For example, the other one of age versus height. It is height that depends on age. One age is independent, whereas height is dependent. So that should be very clear. Quite often, depending on the objective you have, one variable at one time can be independent, whereas in the next analysis it is the outcome. So contextualize it to your research that you're doing. So let's visualize what these three questions are. For purposes of the illustration, we are going to start with the question of what is the test supposed to do. Then we'll look at what type of data do we have, how many groups, and then we'll see which tests. So to start with, what is the test supposed to establish? This can simply be a difference or a relationship. To help us understand these two concepts very well, I'm going to use an example which is very common with many researchers. Most times, many people are looking for factors associated with a certain outcome as their objective or a specific objective stroke research question in their research. And that when they are looking at factors associated with that outcome, the outcome can either be numeric, for example, viral load, weight gain in kilograms, or maybe performance of students. Sometimes the outcome is categorical, stroke nominal, such as someone's looking at factors associated with TB, and TB status is measured as either positive or negative. Someone can be looking at the factors associated with malaria. Malaria is either negative or positive, or sometimes it can even be medication adherence, being measured as someone who adheres and someone who is non-adherent. On the other hand, for the factors associated, they may be also having several of them. For example, someone may be looking at factors like gender, marital status, or age group, which are categorical, or sometimes these factors are numerical. For example, age, if the age is not categorized, it can be income or the distance to the health facility. Now, let's tease out factors associated with weight gain as our specific objective, and our weight gain is numerical. And we are going to point out 4 factors associated with this weight gain of ours. We are going to look at gender and marital status as the categorical variables that we want to associate with weight gain. On the other hand, we are also going to look at age and income, which are numerical variables that we want to see it is their association with weight gain. So let's start with looking at the first factor, gender versus our weight gain. One person may ask themselves, I want to know whether there is a relationship between gender and weight gain. At the end of the day, this person wants to find out, is being male or female, is it related to having higher weight gain? So in that case, is looking at a relationship. Looking at gender as a factor associated with weight gain in this case is a relationship. But if we flip the coin, the person on the other side may also ask themselves, by twisting just this question a little bit, and they ask themselves, is the mean weight gain for males different for that of females? If I obtained the average weight gain of males and I subtracted from that of females, would there be a difference, or the difference would be 0 when they are the same? So the same factor, gender, being looked at as being associated with weight gain, the question is twisted, is presented in 2 different ways, and therefore that question becomes or qualifies to be both a difference and a relationship. So this is the general, so this is applicable to every question you are trying to assess that looks at a categorical variable, any question that looks at a categorical independent variable and a numerical dependent variable. In this case, our weight gain, the dependent variable is numerical, versus gender, our independent variable, which is categorical. So whenever you have such an arrangement, that relationship or that question that you are attempting to answer can both be seen as a difference or a relationship, depending on the context of your research. It is because of this reason that in a short moment we shall be seeing that the categorical arm of our diagram, the categorical arm of the difference and the categorical arm of the relationship are actually the same. So this makes things a little bit easier now. So now let us look at the other 2 sets of factors, age and income versus our weight gain. Starting with age. If you look at age, it is a numerical variable, whereas weight gain is also a numerical variable. Age, being a number, can have very many values ranging from 1 onwards up to maybe 200, depending on how you designed the study. And we can't make a comparison of weight gain at the different years. Mathematically, that is invalid. Therefore, being a number, the only way you can look at whether age is associated with weight gain, which is also a number, is by plotting a scatter plot. And you put your independent variable on the x-axis and the dependent variable weight gain on the y-axis. Then you see the pattern. As age increases, what happens to weight gain? Does it increase or decrease? So in that case, you're purely looking at a relationship. So when your factor is numerical and your outcome is also numerical, so you are purely looking at a relationship. So a quick tip here is, whenever we are designing research studies, we have what we call research specific objectives, or stroke research questions, how we would prefer to call them. Although we may be tempted to take specific objectives as the smallest possible question you can ask yourself, but if you are going to choose the right test for you to analyze your data, you should break down this specific objective or research question of yours to the smallest units. Here we've seen that for factors associated, we've gone deeper to the individual factors. So each factor is treated as a small research question. So that is the level at which we are answering this question of what is the test supposed to establish, not at the other bigger level of the specific objective how it was stated, but inside that specific objective of factors we are treating each factor as a question. Now that you know that your test may be establishing a difference or a relationship, let's now take a closer look at if our question was establishing a difference. If our data is numerical, what type of data do we have? Is our data numerical or categorical? If our data is numerical, in our previous example we just seen say age, which is numerical, and our outcome weight gain is also numerical, we could go ahead and test the assumptions of parametric tests. If they are fulfilled, then we are going to use parametric tests. If any of the assumptions of parametric tests fail, then you would think of using non-parametric tests. Assuming our assumptions have passed, the next or the third question we are asking ourselves is, how many groups are we comparing? For us to answer this question, let's first interpret the meaning of difference and relationship in the ordinary way, in a layman's language. A difference can only exist when there are at least two things. A relationship similarly can only be established if there are two things. Now, in our context, those two things are the variables. If at least there are two variables, or if a variable has at least two groups, maybe you're looking at variables like age and gender, yes, those are two. You're looking at gender versus your outcome, which is the weight gain, those are the two variables. Or you may be looking at groups of a certain variable, gender, which is having male and female. So when we are looking at a difference, we start with assuming or looking at the smallest number possible for a difference to be obtained, which is 2. So your two variables or your two variables obtained from the sample, they can fall under two of these categories. Your data may be paired. By paired, we have two or more measurements on the same individuals. For example, if we measure the body weight of 10 individuals before we start them on a certain intervention of diet, which is aimed at reducing their weight, then we follow up on those very people and we take their measurements after maybe a month. Because both measurements, the before measurements and then the after measurements, are obtained on the same individual, that is referred to as paired. The observations or your data are paired. But take a scenario if we measured the body weight of participants only once, but we want to determine if there is a difference in the mean weight of the males compared to females. Those are unpaired observations. And if your data belong to the first case, where the same individuals were measured at two different time points, we would use a paired t-test. But if the observations are unpaired, then we would use an independent t-test. You notice that in both groups, if we are comparing two groups, if we are looking at a difference in numerical data for variables that have fulfilled the assumptions for parametric tests, we are using a t-test. But the t-test has two versions. A paired t-test that puts into considerations that these are the same people being measured at different time points, whereas the independent or unpaired t-test takes into considerations that these are totally unrelated samples. Now there comes another question. What if we have just said that if we are comparing two groups, we are using a t-test? What if we had more than two groups that we are comparing? Instead of just males, females, the variable was maybe marital status, which had single, married, and separated, and there are now three groups. So instead of the paired t-test if the observations, for example, in this case, were taken before, then at 1 month, at 3 months, maybe, and at 6 months. Same individuals, but measurements are for 4 different time points. Then we would use a repeated measures ANOVA. If the observations were independent, and maybe we are looking at, like I've just said, we are comparing the married, single, and the separated, that we would use one-way ANOVA. Look at ANOVA in full, it is analysis of variance. Look at ANOVA as an extension of t-tests. Like it is ANOVA is like doing several t-tests. Now, what if our data, when we tested for the assumptions of parametric tests, the normality, covariance, and the others, our data did not pass those assumptions? Then it would mean we would explore the non-parametric tests. These parametric tests, so these non-parametric tests, for each of the parametric tests, there is always an alternative non-parametric that you would use. If your data was paired and you would have used the paired test, but because it doesn't meet the requirements of a t-test, which is a parametric test, the alternative non-parametric test you would use is Wilcoxon signed rank or the sign test. You could use this instead of the paired t-test. But if your observations were unpaired and your data, you cannot use the independent t-test, then the alternative non-parametric test would be the Wilcoxon rank sum test. Still, if you had more than 2 groups for paired observation, you are looking at measurements at 3 or different time points for the same participant. Instead of repeated measures ANOVA, you would use the Friedman test. And if they were independent or unpaired observations, instead of one-way ANOVA, you could use the Kruskal-Wallis test. Okay, so things are now interesting. Now we've looked at how to select a statistical test. If you were looking at, if you are looking for a test that establishes a difference, and your data is numerical. What if your outcome variable was categorical? Still, you would ask yourself, is my data paired or unpaired? Categorical, take for instance, if in our example we are using, instead of weight gain being considered as numerical, the weight has been, if we decided to categorize this weight, and maybe say someone is having normal weight, or someone's having overweight. If we first count, before we start giving this diet, we first count the number of people we have, and we find out how many are obese, how many are not. Then we put them on treatment. Then after some time, maybe 6 months, we go back to this population of ours, and then we measure their weights again and categorize them. We want to see how many were obese before and are still obese or overweight after the 6 months. How many were not, or how many were obese but have turned, they are no longer. So our outcome is categorical. In that case, we would use the McNemar test because our data is paired. Same individuals before and after, but we are looking at proportions. Which percentage had overweight before, and then which percentage is having overweight after. But if we had just collected data from independent samples, or if our data is unpaired, we've just gone and we are looking for factors associated with the overweight, then we could use a chi-square test. So this chi-square test can also be further broken down depending on whether there is a natural order in your categories of your outcome or not. For example, if we had our outcome as maybe stages of cancer, stage 1, stage 2, stage 3, where you move from one, there is some inherent order in the categories of your outcome, then you would use chi-square for trend. It puts into consideration that order. But if the categories are not ordered, just have normal and overweight, then you could use the chi-square test for independence. We also have a special type of chi-square where you are establishing a difference between two categorical variables, but you have some other third variable which you would like to also see if it has an effect on this association here. So that potential extraneous variable or third variable can be adjusted for using the Mantel-Haenszel Chi-square test. That is all about selecting a statistical test. If your question attempts to establish a difference for whether you have numerical or categorical data. Let's now turn to what if our aim was to establish a relationship. So if our question is to establish a relationship using our early example of age versus weight gain, where both are numerical, we check for the assumptions of using parametric tests if they are fulfilled. If yes, we use parametric test, and in this case it will be a correlation analysis. A correlation using Pearson's correlation coefficient or regression. Later on we shall be looking at the different regression methods and how to choose a regression method, the one which is most appropriate. And if your numerical data does not meet the assumptions for parametric test, then the non-parametric alternative for Pearson's correlation coefficient is Spearman's correlation. On the other hand, if you had categorical variable, like we said before, the arm is still the same. When you are looking at a categorical independent variable versus a numerical outcome, it is both a relationship and a difference depending on how you twist the question. In the first case, we were asking ourselves, is there a difference in the mean weights of males and females? Here, under relationship, we are asking ourselves, is there a relationship between gender and weight gain? Same question presented differently. So, if the observations are paired, we use the McNemar test. If they are unpaired, we use the chi-square test. And if there is no order, and if there is no inherent order in your outcomes, you can use the chi-square test for independence, whereas if there is order, you can use the chi-square test for trend. And if you, besides the two categorical variables that you are assessing, if there is a third extraneous variable, you can use a special kind of chi-square called the Mantel-Haenszel Chi-square. So far we have looked at a number of tests. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So with this, you are able to effectively apply 15 statistical tests accurately without making any errors. Next, we look at what if our test. So next, we look at a scenario where we have one sample. For instance, if we have like 10 participants where we've collected their weight, we calculate that mean weight, and then we are comparing it to a hypothetical mean of a certain population given to us to see whether the mean we've obtained from these 10 participants is significantly different from the hypothetical mean. Or if it is a categorical variable, we've obtained a proportion of people who maybe have malaria from our sample, but we want to determine if there is a significant difference from a hypothetical population proportion which is out there already known. So if our data is numerical, we've tested still for assumptions of parametric. If they pass, we use a one sample t-test. Whereas if they don't pass, the alternatives Wilcoxon sign rank or the sign test. If our data is categorical, we use the chi-square goodness of fit or the one proportion ZT test. One other thing to note about a chi-square is that for a chi-square, it can accommodate more than two groups. It can do an analysis where your outcome has more than two groups, which is not the case with a one proportion Z test or the case of a McNemar test. So chi-square can accommodate more than two groups. So with this, So in our subsequent videos, we shall be covering how to run these tests, how to run these assumptions, how to interpret the results of these tests, and how to write them in your report using several softwares. We shall be using Stata, shall be using SPSS and other softwares. See you in the next video of descriptive statistics. In order not to miss out any of our episodes, please subscribe to our Analytics YouTube channel and stay posted.